Okay, so now we're going to talk about recurrence relations. So this is not only seen in computer science, but also math. And basically what we're doing is we're giving a function, in this case to represent the runtime of an algorithm on input size n, but this function depends on the runtime of the algorithm on a smaller input. So these are recursive functions. If you're familiar with math, think about the Fibonacci numbers, how one number depends on the two numbers before it. This is a very similar concept. So the technique for this is just you keep on plugging in to your equation that you have and simplify until you reach your base case. So the way we're going to solve that is with some examples here. And we'll assume that t of 0 equals 1 and t of 1 equals 1. So that's just saying, in this case, like on an input size of 0, the time it takes is constant, it's 1. And similarly, on an input size of 1, it takes constant time, our algorithm. So suppose we say that our algorithm, the time it takes for it to run on an input size of n, it's equal to t of n minus 1, so the time it takes to run on input size of 1 smaller, plus some constant k. So we want to simplify this into our big O notation. So the way we'll do that is we'll take this t of n minus 1 term and plug it into here. So that'll give us t of n minus 2, let me just write it out. Where we see an n, we're going to put it in n minus 1. So n minus 1 minus 1 plus k, and then we're going to add the k from before, right? So we started out with this, and then we wanted to simplify this. So we took this n minus 1, plugged it into here. So when we plug that into here, we get t of n minus 1 minus 1 plus k. So that's this entire term. And then we still have to add this plus k from before, so that's that. Okay, so that's equal to t of n minus 2 plus 2k. Then we'll do the same thing, plug in this n minus 2, and we get t of n minus 2 minus 1 plus k, and then add the 2k from before. This simplifies to t of n minus 3 plus 3k. And you can do it again, and you'll see that this is n minus 3 minus 1 plus k plus 3k equals t of n minus 4 plus 4k. And you're starting to see a pattern, and eventually we'll get down to like t of n minus q plus qk. That's sort of the pattern we're following here, right, where we have this minus 4 plus 4k, minus 3 plus 3k, minus q plus qk. And we have it in terms of these variables because we want to hit our base case of 0 or 1, right? So in this case, let me use orange. When q equals n, we have t of n minus q plus qk is equal to t of n minus n plus nk. That's going to be equal to t of 0 plus nk, which is equal to 1 plus nk, and that we're going to say is big O of n. All right, so we just did a lot of stuff here. We have our generic formula, which is great, right? We said t of n is now equal to this for for any q, really. Now that's great and all, but it's still like a recurrence relation. This t of n is still defined as t of some other quantity. But we know that we can get rid of this once we hit 0 or 1. So let's just say this inner quantity is 0, and that occurs when q equals n. So when q equals n, we plug n for q back into here. We get t of n minus n plus nk, that's t of 0 plus nk, and that's 1 plus nk by our definition. And so this, we said, is equal to t of n, right? That's what we started out with, and eventually we get down to here. So if t of n is equal to this expression right here, well, we can just look at this, pretend this is our function, and analyze the runtime of that. This constant term doesn't matter. We have a constant times n, so it's big O of n. So we sort of just plug things in repeatedly until we hit our base case, take a look at the function that we have left, and then assign its big O value. Let's do another example to see what happens, and then hopefully it'll start to make sense. So t of n equals 2 times t of n minus 1 plus k. So it's very similar to the previous example, except now we have this constant 2 here. So let's see how things change. Well, we'll keep the 2. For t of n minus 1, we're gonna substitute n minus 1 into here. So that will give us 2 times t of n minus 1 plus k, and then we're going to add the k from before. So we can simplify this. This will be 2 squared times t of n minus 2 plus 2k plus k. All right, so now let's try to simplify that t of n minus 2 term. So we get 2 squared times 2 of t of n minus 2 minus 1 plus k. I need to get rid of this parentheses. Plus the 2k plus the k. This simplifies a little bit to 2 cubed plus t times n minus 3 plus 2 squared k plus 2k plus k. So maybe you're starting to see a small pattern. Let's try to do one more. So 2 cubed, 2 times t of n minus 3 minus 1 plus k plus 2 squared k plus 2k plus k. And this simplifies to 2 to the 4th times t of n minus 4 plus 2 cubed k plus 2 squared k plus 2k plus k. And then hopefully you're starting to see the pattern now. So eventually we'll reach down to 2 to the q times t of n minus q plus 2 to the q minus 1k plus 2 to the q minus 2k plus all the way down to 2k plus 2, right? So this is our first term here. We have the q, which is 4. Then we subtract it inside, that's good. And then we're just adding on these powers of 2 multiplied with k. And we start with 2 to the q minus 1, decrease by 1 all the way down to 2. This should be a k. Let me change that. Right? So that's sort of the general formula that we have to deal with here. So this is a little bit more complex to work with and not as fun. So again, it's a good question to see, when does this bottom out? Meaning, when can we get rid of this term entirely? So when q equals n, t of n minus q is equal to t of n minus n, which is equal to t of 0, which is equal to 1. So let's substitute q equals n, and we get 2 to the n times 1, because we just solved for t of n minus q, plus 2 to the n minus 1k, plus 2 to the n minus 2k, plus plus 2k, plus k. So this first term will leave as 2 to the n. And the remaining things, I can factor out a k, and then that's just the sum of powers of 2. So I'm going to write this as a summation of 2 to the, I'll use the letter I, and we go from I equals 0, because this is 2 to the 0 times k, and then we go to 2 to the 1 times k, all the way up till n minus 1. Right? And hopefully we remember our equations for the sum of this powers series. That's going to simplify to 2 to the n minus 1. That is how we simplify that. And then we can simplify this a little bit more. This is 2 to the nk minus k. And again, we want to look at our n terms here. This constant doesn't matter. Here we have both of these are 2 to the n terms. So we conclude that this is big O of 2 to the n. So let's just take a moment to analyze the differences. So here, in our previous example, without that power, or without that constant 2 before it, we concluded that it was big O of n, which means the algorithm ran in linear time, which is really, really good. What this means is like, it takes O of n time to read an input. So in order, like, to have an algorithm that runs that quickly in the time it takes to read an input, that's pretty fantastic. Just by adding this constant 2 here, we get big O of 2 to the n. This is an exponential time algorithm, which is terrible. Terrible. So for example, let's compare this to big O of n. Choose your value of n, like 10. Would you rather have a time that, like an algorithm that runs in time O of 10, whatever that means, or O of 2 to the 10, which is equal to O of 1024? Like, we don't really know, we kind of understand what these quantify, but like, we're looking for the more efficient algorithms. We're looking for the smaller value. O of 10 is clearly better here, by a lot. And we just chose n equals 10, which is not even a big number at all. So as we get even bigger and bigger, they just don't compare. Let's just take a look at the graphs of n versus 2 to the n. So n is a straight line that looks like this. 2 to the n looks like this. So not even close. This just grows way too quickly, whereas n grows slowly and steadily. So big O of n is fantastic compared to 2 to the n. Always avoid this. Let's do another example. So here, t of n equals t of n over 2 plus k. Again, k is a constant. So do the same technique. T of n over 2, I'll substitute that back in. So that'll give me t of n over 2 divided by 2. That looks really annoying. But plus k, and then we add the k. So that's equal to t of n over 2 squared plus k, and that's just t of n over 2 squared plus 2k. All right, so let's plug that back in. T of n over 2 squared divided by 2 plus k plus 2k. It's going to be equal to t of n over 2 cubed plus 3k. All right, small pattern forming. Let's do one more. T of n over 2 cubed divided by 2 plus k plus 3k is equal to t of n over 2 to the 4th plus 4k. All right, so now we see the pattern. So we'll generalize this to t of n over 2 to the q plus qk. So when does this bottom out? When n over 2q equals 1, we'll have t of n over 2 to the q will obviously be equal to t of 1, which is equal to 1. So that's when we can get rid of this t term. So when does that occur? Kind of have to solve for q here. So that occurs when n equals 2 to the q, or alternatively, when q equals log base 2 of n, which I'll denote as lg of n. So now we have found our value for q, for which this t term goes away, so let's substitute it back in. N over 2 to the log of n plus log of n times k. That's going to be equal to t to the n. 2 to the log base 2 of n will just be n plus k log n. That's t of 1 plus k log n. We said t of 1 is 1. So overall, our algorithm is O of log n. And O of log n is actually fantastic. And we will be exploring an algorithm momentarily, which is O of log n. O of log n is actually more efficient than O of n. So yeah, that's another example of analyzing recurrence relationships and seeing what their big O notation is. Great.